In the outer reaches of our solar system, where the sun appears as merely a bright star and the cold of space permeates everything, orbits one of the most beautiful objects in the cosmos, Saturn, the ring jewel of our celestial neighborhood. Tonight we drift alongside the Cassini spacecraft on its 13-year journey of discovery, witnessing the intricate dance of billions of ice particles that create the most spectacular ring system known to science. Saturn's rings have captivated humanity since Galileo first glimpsed them through his primitive telescope in 1610, though he couldn't quite understand what he was seeing. It wasn't until 1659 that Christian Huygens correctly identified them as a ring system surrounding the planet. For centuries, these rings remained a distant mystery, beautiful but unknowable, like a crown of ice and starlight circling the golden giant. The Cassini mission, launched in 1997, transformed our understanding of Saturn's rings from simple bands of material into a complex dynamic system of incredible beauty and sophistication. For 13 years, this robotic explorer studied the Saturnian system, sending back images and data that revealed the rings to be far more intricate than anyone had imagined. The rings stretch across nearly 300,000 kilometers, 3/4 of the distance from Earth to the Moon, yet they are astonishingly thin, in some places only a few meters thick. Imagine a sheet of paper scaled up to the size of a football field, and you begin to appreciate the delicate proportions of Saturn's rings. They are composed primarily of water ice, ranging from tiny particles no bigger than dust grains to house-sized chunks, all orbiting Saturn in perfect harmony. What appears from Earth as a simple system of concentric rings is actually composed of thousands of individual ringlets, each following its own orbital path. The rings are named with letters in order of their discovery: the bright A and B rings, separated by the Cassini division, the faint C ring, and the extremely tenuous D, E, F, and G rings. Each ring has its own character, its own story written in the language of gravitational dynamics and particle collisions. The F ring, discovered by Pioneer 11 in 1979, proved to be one of the most dynamic and mysterious components of the ring system. This narrow ring, only a few hundred kilometers wide, is shepherded by two small moons, Prometheus and Pandora, which gravitationally sculpt its shape. The F ring displays kinks, braids, and bright clumps that change over time scales of hours to months, creating a constantly evolving sculpture in ice and stone. Cassini revealed that the rings are not static but alive with activity. When propeller features, caused by embedded moonlets, create gaps and disturbances in the ring material. Spokes, mysterious radial features first discovered by the Voyager spacecraft, appear and disappear in the B ring, possibly caused by electromagnetic forces interacting with microscopic dust particles. The rings also sing. Cassini detected radio emissions from Saturn's magnetosphere interacting with the ring particles, creating eerie sounds that were converted to audio files for human ears. These, and sounds of Saturn, include whistles, chirps, and haunting melodies that seem to emerge from the cosmic dance of charged particles and magnetic fields. One of Cassini's most spectacular discoveries was the source of Saturn's E-ring. This diffuse ring, which extends far beyond the main ring system, is continuously replenished by geysers erupting from the south pole of Enceladus, a small icy moon. These geysers shoot water, ice, and organic compounds hundreds of kilometers into space, creating the material that forms the E-ring and suggesting that Enceladus harbors a subsurface ocean beneath its icy crust. The shepherd moons that help maintain the ring structure are worlds of wonder themselves. Pan, orbiting within the Encke gap in the A-ring, has accumulated ring material around its equator, giving it the appearance of a flying saucer. Daphnis, orbiting in the Keeler gap, creates waves in the ring edges that ripple outward like the wake of a boat moving through water. Titan, Saturn's largest moon, plays a crucial role in the dynamics of the entire system. This moon, larger than the planet Mercury, has a thick atmosphere of nitrogen and methane, with lakes of liquid hydrocarbons on its surface. Titan's gravitational influence helps shape the outer regions of the ring system and creates resonances that maintain gaps and divisions in the rings. The origin of Saturn's rings remains one of the great mysteries of planetary science. They may be the remnants of a shattered moon, destroyed by tidal forces or a catastrophic collision. Alternatively, they might be composed of material that never coalesced into a moon, left over from the early formation of the Saturnian system. The ring's relatively young age, perhaps only 100 million years old, suggests they are a recent addition to Saturn's family, a cosmic accident that created one of the most beautiful sights in the solar system. During its final mission phase, Cassini made a series of daring dives between Saturn and its rings, providing unprecedented close-up observations of the ring system. These and grand finale orbits revealed that the rings are raining material onto Saturn's atmosphere, gradually eroding away over time. The rings we see today are a temporary phenomenon, destined to disappear over the next few 100 million years. The chemical composition of ring particles, as revealed by Cassini's final plunge through the system, showed surprising complexity. The rings contain not just water ice, but also organic compounds and rocky material, suggesting a more complex origin than previously thought. Some ring particles appear to be fluffy aggregates of smaller pieces, while others are solid chunks of almost pure ice. The seasonal changes on Saturn create variations in the ring system as well. As Saturn orbits the Sun over its 29-year cycle, the rings appear to open and close from Earth's perspective, creating different lighting conditions. These seasonal changes affect the temperature and behavior of ring particles, causing subtle variations in the ring's appearance and structure. Saturn's rings also create their own weather systems. Temperature variations across the rings create convection-like processes that transport material vertically, while electromagnetic forces can lift small particles above the ring plane. These processes create the complex three-dimensional structure that gives the rings their incredible beauty and diversity. As you close your eyes tonight, imagine drifting through Saturn's rings alongside tiny ice particles, each one catching and reflecting the distant sunlight. Picture the gravitational dance of countless particles, shepherded by small moons and shaped by resonances with larger satellites. Envision the delicate balance that maintains this cosmic symphony, where every particle plays its part in creating one of the most beautiful sights in the universe. Saturn's rings remind us that beauty exists on cosmic scales, that the universe contains wonders beyond our wildest imagination. They are a testament to the power of gravity to create order from chaos, to transform simple materials into structures of breathtaking complexity and elegance. In their ephemeral beauty, they teach us that even the most magnificent cosmic phenomena are temporary, making them all the more precious and worthy of our wonder. The rings of Saturn will continue their celestial dance for millions of years to come, gradually changing and evolving as they spiral slowly toward the planet. They are a reminder that we live in a dynamic universe where even the most seemingly permanent features are part of an ongoing story of creation and destruction, beauty and transformation. As we drift toward sleep, we can take comfort in knowing that somewhere in the darkness of space, Saturn's rings continue their eternal dance, a symphony of ice and stone that plays on scales both vast and intimate, creating music that resonates through the cosmos itself. In the vast spaces between stars, where darkness might seem to reign supreme, lie some of the most spectacular and life-giving regions in the universe, stellar nurseries where new stars are born from cosmic dust and gas. Tonight, we drift through these celestial gardens, witnessing the magnificent process by which the universe creates its most fundamental building blocks, the stars that light the cosmic darkness and forge the elements of life itself. These stellar nurseries are called nebulae, from the Latin word meaning on cloud. They are vast regions of gas and dust, primarily hydrogen and helium, stretched across distances that dwarf our solar system. Some nebulae are so large that light, traveling at its incredible speed, takes years to cross from one edge to the other, Yet despite their immense size, these clouds are extraordinarily tenuous. If you could scoop up a cube of nebular material the size of a building, it would contain less matter than a single breath of air. The most famous of these stellar nurseries is the Orion Nebula, visible to the naked eye as a fuzzy star in the constellation Orion. This cosmic cradle lies about 1,400 light-years from Earth and spans roughly 24 light-years across. At its heart lies the trapezium, a cluster of young hot stars whose intense radiation illuminates the surrounding gas, creating a glowing beacon that has inspired astronomers for centuries. The Orion Nebula is a stellar maternity ward where new stars are born at a prodigious rate. Deep within its dusty depths, the Hubble Space Telescope has revealed protoplanetary disks, swirling disks of material around young stars where planets are likely forming. These disks, which astronomers call unenproplids, show us planetary systems in their earliest stages, offering glimpses of how our own solar system might have formed 4.6 billion years ago. The process of star formation is both violent and beautiful. It begins when regions within a nebula become slightly denser than their surroundings, perhaps triggered by the shock wave from a nearby supernova explosion or the gravitational influence of a passing star. These dense regions begin to collapse under their own gravity, slowly at first, then with increasing speed as they become more compact. As the collapsing material falls inward, it begins to heat up due to gravitational compression. The center of the collapsing cloud becomes a protostar, a hot, dense object that has not yet begun nuclear fusion but glows with the heat of gravitational contraction. The protostar is surrounded by a disk of material that spirals inward, feeding the growing star and potentially forming planets. The Eagle Nebula, made famous by the Hubble Space Telescope's iconic and Pillars of Creation photograph, shows us star formation in action. These towering pillars of gas and dust, each several light-years tall, are being sculpted by the intense radiation from nearby young stars. At the tips of these pillars, new stars are being born, their formation triggered by the very radiation that is slowly eroding the pillars away. The colors of nebulae tell the story of their composition and the stars within them. Red regions typically indicate hydrogen gas excited by ultraviolet radiation from hot young stars. Blue areas often show reflected light from dust particles, while green regions can indicate the presence of doubly ionized oxygen. These colors create cosmic paintings of extraordinary beauty, each one unique in its combination of chemistry, physics, and stellar influences. Not all nebulae are stellar nurseries. Some are the cosmic equivalent of funeral pyres, planetary nebulae created when dying stars shed their outer layers into space. The Ring Nebula in Lyra and the Helix Nebula in Aquarius are examples of these stellar death announcements, where the central white dwarf star illuminates the shell of gas it expelled during its final moments as a red giant. The Crab Nebula represents perhaps the most dramatic type of stellar death, a supernova remnant. This expanding shell of gas and debris was created when a massive star exploded in 1054 AD, an event so bright that it was visible during daylight for 23 days. Chinese astronomers of the time called it a guest star, not knowing they were witnessing one of the most energetic events in the universe. The Horsehead Nebula, one of the most recognizable silhouettes in the sky, shows us the interplay between different types of nebular material. This dark nebula is a dense cloud of dust and gas that blocks the light from the bright emission nebula behind it, creating a striking equine silhouette against the glowing background. The contrast between light and shadow creates a sense of depth and drama that rivals any earthly landscape. The Rosette Nebula, shaped like a cosmic flower, demonstrates how stellar winds from young hot stars can carve cavities in the surrounding gas. The central cavity, about 50 light-years across, was blown clear by the intense radiation pressure from the cluster of stars at its heart. The remaining gas forms delicate petals around the edge, glowing with the characteristic red light of excited hydrogen. Modern space telescopes have revealed that many nebulae are far more complex than they appear in visible light. The Spitzer Space Telescope's infrared vision could peer through dust clouds to reveal the cool, dense cores where stars are about to be born. The James Webb Space Telescope now provides even more detailed views, showing the intricate structures within star-forming regions and the processes that govern stellar birth. The star formation process creates not just individual stars, but entire stellar communities. Open star clusters, like the Pleiades, are groups of stars born from the same nebular cloud. These stellar siblings share similar compositions and ages, slowly drifting apart over millions of years as they orbit the galaxy. The brightest stars in these clusters often have short lives, exploding as supernovae and enriching the surrounding space with heavy elements. These heavy elements, carbon, oxygen, silicon, iron, and others, are crucial for the formation of planets and life. They are forged in the nuclear furnaces of stars and dispersed into space when stars die. This recycled material becomes part of new nebulae, enriching them with the elements necessary for rocky planets and organic chemistry. We are literally made of star stuff, our bodies composed of elements created in the hearts of long-dead stars. The interstellar medium, the space between stars, is not empty but filled with this enriched material. Supernova explosions create bubbles of hot gas that push against the cooler surrounding material, creating the complex structures we see in nebulae. These shockwaves can also trigger new rounds of star formation, creating a cycle of stellar birth and death that is continued for billions of years. As you drift toward sleep tonight, imagine floating through these cosmic gardens where stars are born. Picture the slow dance of gravity as it gathers diffuse gas into dense cores, the moment when nuclear fusion ignites and a new star begins to shine. Envision the delicate beauty of these stellar nurseries, where chaos and order combine to create the most fundamental structures in the universe. These nebulae are not just distant objects to admire, they are the factories where the universe creates its future. Every star that will ever shine, every planet that will ever form, every element that will ever contribute to life, begins its journey in these vast cosmic clouds. In their beauty and complexity, they remind us that we are part of an ongoing story of creation that spans billions of years and countless light years. The nebulae continue their work even as we sleep, gravity slowly gathering material into new stars that will light the universe for millions or billions of years to come. They are the ultimate expression of cosmic creativity, turning the simple elements of hydrogen and helium into the complex chemistry of stars, planets, and life itself. In their gentle glow and intricate structures, they whisper the secrets of cosmic evolution, telling us that the universe is not just vast and ancient, but also creative and beautiful beyond measure. In the deepest reaches of space, where the laws of physics strain against the boundaries of our understanding, lie some of the most enigmatic and powerful objects in the universe, black holes. Tonight, we venture into these cosmic mysteries, exploring regions where space and time become so warped that reality itself seems to bend and twist in ways that challenge our most fundamental assumptions about the nature of existence. A black hole is not truly a hole at all, but rather a region of space where gravity has become so intense that nothing, not matter, not light, not even information itself, can escape once it crosses the event horizon. These cosmic giants are born from the death of massive stars, when stellar cores collapse under their own gravity to create points of infinite density called singularities. The story of black holes begins in the early 20th century with Einstein's general theory of relativity, which predicted that massive objects could warp space-time so severely that they would create these inescapable gravitational prisons. For decades, they remained theoretical curiosities, mathematical solutions to Einstein's equations that seemed too strange to exist in the real universe. The first strong evidence for black holes came from 10-ray observations of binary star systems, where an invisible companion was stripping material from a visible star. As matter spirals into a black hole, it forms an accretion disk that heats up to millions of degrees, glowing brilliantly in X-rays. These cosmic lighthouses, ironically, revealed the presence of objects so dark that they absorb all light that approaches them. Cygnus 61, discovered in 1964, was the first widely accepted black hole candidate. This system contains a blue supergiant star orbiting an invisible companion with a mass too great to be a neutron star. The only explanation that fits the observations is that the companion is a black hole, consuming material from its stellar partner in a gravitational dance that has continued for millions of years. The supermassive black holes that lurk at the centers of galaxies are among the most massive objects in the universe. These cosmic titans can contain the mass of millions or billions of suns, yet they are compressed into regions smaller than our solar system. The black hole at the center of our own galaxy, Sagittarius A, contains about 4 million solar masses and lies hidden behind dense clouds of dust and gas. In 2019, the Event Horizon Telescope achieved what many thought impossible. It captured the first image of a black hole's event horizon. The target was M87, the sentient supermassive black hole 55 million light-years away at the center of the galaxy M87. The image showed the black hole's shadow silhouetted against the glowing accretion disk, confirming Einstein's predictions about how extreme gravity warps the fabric of space-time. The Event Horizon Telescope's achievement required linking radio telescopes around the world to create a virtual telescope the size of Earth. The resulting image showed the characteristic ring of light around the black hole's shadow, with one side appearing brighter than the other due to the relativistic effects of the spinning accretion disk. This image provided direct visual evidence of the event horizon, the boundary beyond which nothing can escape. Black holes are not cosmic vacuum cleaners that suck in everything around them. Objects must cross the event horizon to be captured, and this boundary is not a physical surface, but rather a point of no return defined by the escape velocity reaching the speed of light. From a distant observer's perspective, time appears to slow down near the event horizon due to gravitational time dilation, creating the illusion that matter falling into the black hole freezes at the boundary. The environment around black holes is one of the most extreme in the universe. Near the event horizon, tidal forces can stretch objects into long, thin shapes, a process colorfully called unspaghettification. The accretion disks around black holes can reach temperatures of millions of degrees, creating jets of material that shoot outward at nearly the speed of light, extending for thousands of light-years into space. These relativistic jets are among the most powerful phenomena in the universe, capable of influencing the evolution of entire galaxies. The energy released by material falling into a black hole can exceed the total energy output of billions of stars, making active galactic nuclei some of the brightest objects in the cosmos. Quasars, the most luminous objects known, are powered by supermassive black holes consuming vast amounts of material. The study of black holes has revealed profound connections between seemingly unrelated areas of physics. The information paradox, the question of what happens to information that falls into a black hole, has led to new insights about the nature of quantum mechanics and the structure of spacetime. Stephen Hawking's prediction that black holes emit radiation and eventually evaporate has revolutionized our understanding of the relationship between gravity and quantum mechanics. Stellar mass black holes, formed from the collapse of massive stars, represent the final stage in stellar evolution. When a star more than 20 times the mass of our Sun exhausts its nuclear fuel, the core collapses in less than a second, creating a black hole. The outer layers of the star are blown away in a supernova explosion, while the core becomes a gravitational singularity where the laws of physics as we know them cease to apply. Intermediate mass black holes, with masses between those of stellar mass and supermassive black holes, have only recently been confirmed to exist. These mysterious objects may form through the merger of smaller black holes or the direct collapse of massive gas clouds in the early universe. They represent a missing link in our understanding of how supermassive black holes grew to their enormous sizes. The detection of gravitational waves by LIGO and Virgo has opened a new window into the black hole universe. These ripples in spacetime created when black holes merge carry information about the masses and spins of the colliding objects. The first gravitational wave detection in 2015 confirmed the existence of stellar mass black holes and demonstrated that they can spiral into each other and merge, creating even more massive black holes. Black holes play a crucial role in the formation and evolution of galaxies. The supermassive black holes at galactic centers appear to be intimately connected to the properties of their host galaxies. The mass of a central black hole correlates with the mass of the galaxy's bulge, suggesting that black holes and galaxies evolve together through cosmic time. The paradoxes associated with black holes continue to challenge our understanding of physics. The holographic principle suggests that all the information about a black hole's interior may be encoded on its two-dimensional surface. This idea has profound implications for our understanding of space, time, and information, suggesting that the three-dimensional world we experience may be a projection of information stored on a two-dimensional surface. As you prepare for sleep tonight, imagine the invisible guardians that patrol the cosmic deep, black holes whose gravitational influence shapes the architecture of the universe. Picture the spiral dance of matter around these cosmic titans, the jets of energy that stream away at nearly the speed of light, and the profound warping of space-time that makes clocks run slow and rulers shrink near the event horizon. Black holes remind us that the universe contains phenomena that exceed our everyday experience and challenge our most fundamental assumptions about reality. They are laboratories for testing the limits of physics, cosmic engines that power the most energetic phenomena in the universe, and the ultimate expression of gravity's power to shape space and time. In their mysterious depths, black holes hold the secrets of stellar death and galactic evolution, the nature of space-time and the limits of knowledge itself. They are the universe's most extreme objects, where the familiar laws of physics give way to stranger truths that we are still learning to understand. As we drift toward sleep, we can find comfort in knowing that these cosmic guardians continue their eternal vigil, shaping the universe through their immense gravitational influence and reminding us that even in the deepest darkness, there is profound beauty and meaning to be found. In the silent hours before dawn, when the veil between night and day is thinnest, we turn our attention to the most profound questions that have ever stirred the human imagination. How did the universe begin? What were the first stars like? How did the cosmic structures we see today, galaxies, clusters, and the vast web of dark matter, emerge from the smooth simplicity of the early universe? Tonight, we embark on a journey through deep time, guided by the most powerful telescopes ever conceived. These magnificent instruments are not just tools for observation, but time machines, allowing us to peer back across billions of years to witness the universe in its infancy. As light from distant galaxies travels across the cosmos, it carries with it the story of cosmic evolution, written in wavelengths of electromagnetic radiation that speak to us across the vast distances of space and time. The story of our cosmic origins begins with the cosmic microwave background, the afterglow of the Big Bang itself. This faint radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1965, permeates the entire universe and represents the oldest light we can observe. When this radiation was emitted, about 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely through space for the first time. The cosmic microwave background is not perfectly uniform but contains tiny fluctuations, variations in temperature of only a few millionths of a degree. These subtle ripples represent the seeds of all cosmic structure, the slight density variations that would eventually grow under the influence of gravity to become the galaxies and galaxy clusters we observe today. The pattern of these fluctuations encodes information about the fundamental properties of the universe, its age, composition, and ultimate fate. The Hubble Space Telescope revolutionized our understanding of the deep universe through its deep field observations. By staring at seemingly empty patches of sky for hundreds of hours, Hubble revealed thousands of distant galaxies, each one a time capsule from the early universe. The Hubble Deep Field, taken in 1995, showed us galaxies as they appeared when the universe was only a few billion years old. These early galaxies were unlike anything we see in the nearby universe. They were smaller, more irregular, and often engaged in violent mergers and collisions. The Hubble observations revealed that the universe was a much more chaotic and dynamic place in its youth, with galaxies forming and evolving at a rapid pace. Some of these ancient galaxies were already forming stars at rates far exceeding those seen in modern galaxies. The James Webb Space Telescope has taken us even further back in time, revealing the universe as it appeared just a few 100 million years after the Big Bang. Webb's infrared vision can penetrate the dust and gas that obscures the most distant galaxies, showing us the first generation of stars and galaxies to illuminate the cosmic dark ages. These observations have revealed that massive galaxies formed much earlier than previously expected, challenging our understanding of cosmic evolution. Webb's observations have uncovered supermassive black holes that existed when the universe was less than a billion years old. These cosmic titans, containing millions or billions of solar masses, challenge our understanding of how such massive objects could have formed so quickly in the early universe. The existence of these early black holes suggests that the first stars and galaxies grew and evolved through processes we are only beginning to understand. The telescope has also revealed the chemical composition of the earliest galaxies, showing that they contained fewer heavy elements than modern galaxies. This is expected, as the first stars had to form from the primordial hydrogen and helium created in the Big Bang, without the carbon, oxygen, and other heavy elements that are essential for planet formation and life as we know it. One of Webb's most remarkable discoveries is the identification of the most distant galaxies ever observed, appearing as they were when the universe was only 400 million years old. These ancient galaxies are small and compact, containing about 1 billion stars crammed into regions much smaller than our Milky Way. They represent the building blocks that would eventually merge and collide to form the massive galaxies we see today. The study of distant galaxies has revealed that the universe has been expanding at an accelerating rate for the past several billion years. This acceleration is attributed to dark energy, a mysterious force that makes up about 70% of the universe but whose nature remains completely unknown. The discovery of cosmic acceleration earned the 2011 Nobel Prize in Physics and has fundamentally changed our understanding of the universe's fate. The cosmic web, the largest scale structure in the universe, is revealed through observations of distant galaxies and quasars. This vast network of filaments and voids shows how matter is distributed on the largest scales, with galaxies strung along filaments of dark matter like beads on a cosmic string. The cosmic web represents the outcome of billions of years of gravitational evolution, starting from the tiny fluctuations imprinted in the cosmic microwave background. The first stars in the universe, called population 3 stars, have never been directly observed, but are predicted to have been very different from the stars we see today. These primordial stars would have been massive, short-lived, and metal-free, ending their lives in spectacular supernova explosions that enriched the universe with the first heavy elements. Webb and future telescopes may finally detect the signatures of these first stellar generations. The cosmic dark ages, the period between the emission of the cosmic microwave background and the formation of the first stars, represent one of the least understood epochs in cosmic history. During this time, the universe was filled with neutral hydrogen and helium, but no sources of light existed to illuminate the cosmic darkness. The first stars began to form when small density fluctuations in the dark matter collapsed under their own gravity, creating the conditions for star formation. The epoch of reionization, when the first stars and galaxies began to ionize the neutral hydrogen that filled the universe, represents a crucial transition in cosmic history. This process, which occurred gradually over several 100 million years, transformed the universe from a neutral, opaque medium to the ionized, transparent state we observe today. Webb's observations are providing new insights into this cosmic phase transition. The study of distant supernovae has revealed that the universe is not only expanding, but that this expansion is accelerating. Type Ia supernovae, which all reach approximately the same peak brightness, serve as standard candles that allow astronomers to measure cosmic distances. Observations of these stellar explosions in distant galaxies showed that they are fainter than expected, indicating that the universe's expansion is speeding up. As you close your eyes tonight, imagine the ancient light from the most distant galaxies, photons that have traveled for billions of years across the expanding universe to reach our telescopes. Picture the first stars igniting in the cosmic darkness, their nuclear fires beginning the process of creating the heavy elements that would eventually make planets and life possible. The cosmic story revealed by our telescopes is one of remarkable beauty and complexity. From the smooth, hot beginning of the Big Bang to the rich tapestry of galaxies, stars, and planets we see today, the universe has undergone a transformation that spans 13.8 billion years of cosmic time. We are part of this story, made from elements forged in the hearts of stars and assembled on a planet that orbits one of hundreds of billions of stars in our galaxy. The telescopes that reveal these cosmic vistas are humanity's most powerful tools for understanding our place in the universe. They show us not just where we came from, but where we are going as the universe continues to expand and evolve. In their observations of distant galaxies and ancient light, they remind us that we are citizens of a cosmos that is vast, ancient, and filled with wonders that exceed our greatest imagination. As we drift through the quiet hours of night, suspended between the achievements of the past and the promise of tomorrow, we turn our gaze toward the future of space exploration. The cosmos stretches before us, filled with destinations we have yet to visit, mysteries we have yet to solve, and wonders we have yet to discover. Tonight, we explore the next chapters in humanity's greatest adventure, our ongoing journey to understand and explore the universe that surrounds us. The return of humans to the moon through the Artemis program represents a new chapter in lunar exploration, one that promises to establish a permanent human presence on our celestial neighbor. Unlike the Apollo missions of the 1960s and 70s, which were brief visits to demonstrate technological capability, Artemis is designed to create a sustainable presence on the moon, with the ultimate goal of using our lunar experience to prepare for human missions to Mars. Artemis I, the uncrewed test flight of the Orion spacecraft, successfully completed its mission in late 2022, demonstrating that NASA's new deep space exploration systems are ready for human crews. The mission sent an uncrewed Orion capsule on a journey around the moon, testing the spacecraft's systems in the harsh environment of deep space. The successful completion of this mission marked a crucial step toward returning humans to the lunar surface. Artemis II, planned for 2026, will carry 4 astronauts on a journey around the moon, the first humans to travel beyond Earth orbit since the Apollo 17 mission in 1972. This mission will test Orion's life support systems and crew interfaces, preparing for the historic Artemis III mission that will land the first woman and first person of color on the lunar surface. The lunar South Pole, the target for Artemis III, is a region of perpetual mystery and scientific interest. Here, in the depths of permanently shadowed craters, water ice has been preserved for billions of years, representing a resource that could support future lunar settlements and serve as fuel for deeper space missions. The extreme conditions at the lunar poles, where temperatures can drop to minus 240 degrees Celsius and some regions have not seen sunlight for billions of years, create unique opportunities for scientific discovery. The Lunar Gateway, a small space station that will orbit the moon, will serve as a staging point for lunar surface missions and a laboratory for deep space research. This outpost will enable longer stays on the lunar surface and provide experience in operating complex systems far from Earth. The Gateway represents humanity's first permanent outpost in deep space, a foothold beyond Earth's protective embrace. Meanwhile, robotic explorers continue to expand our understanding of the solar system. The Europa Clipper mission, launched in 2024, is now traveling toward Jupiter's moon Europa, where it will conduct the most detailed study ever undertaken of an ocean world beyond Earth. This mission will determine whether Europa's subsurface ocean could support life, using a suite of instruments to study the moon's ice shell, hidden ocean, and thin atmosphere. Europa Clipper will make 49 close flybys of Europa, each pass revealing new details about this fascinating world. The spacecraft will use ice-penetrating radar to study the structure of Europa's ice shell, magnetic field measurements to confirm the presence of the subsurface ocean, and thermal imaging to search for areas where the ocean might be in contact with the surface. If successful, this mission could identify the best locations for future landers that might search directly for signs of life. The Perseverance rover continues its methodical exploration of Mars, collecting samples that will eventually be returned to Earth for detailed analysis. The Mars Sample Return Mission, a collaboration between NASA and the European Space Agency, represents one of the most ambitious robotic missions ever attempted. The samples collected by Perseverance will be the first materials from another planet to be brought back to Earth for laboratory analysis. These Martian samples may finally answer the question of whether life ever existed on Mars. The rocks and soil collected from Jezero crater contain chemical signatures that could preserve evidence of ancient microbial life, if such life ever existed. The analysis of these samples in Earth's most sophisticated laboratories will provide insights into the potential for life on Mars and other worlds. The James Webb Space Telescope continues to revolutionize our understanding of the universe, peering deeper into space and further back in time than ever before. Future observations will focus on the atmospheres of potentially habitable exoplanets, searching for the chemical signatures of life beyond our solar system. Webb's unprecedented sensitivity may finally answer the question of whether we are alone in the universe. The search for life beyond Earth extends beyond our solar system to the thousands of exoplanets discovered by missions like Kepler and TESS. Future missions will study the atmospheres of these distant worlds, looking for biosignatures, chemical markers that could indicate the presence of life. The discovery of life on another planet would represent one of the most profound discoveries in human history. Advances in propulsion technology promise to make interplanetary travel faster and more efficient. Solar sails, which use the pressure of sunlight for propulsion, could enable missions to reach the outer planets more quickly. Ion drives, which accelerate charged particles to create thrust, are already being used on deep space missions and will become increasingly important for future exploration. The development of nuclear thermal and nuclear electric propulsion systems could dramatically reduce travel times to Mars and other destinations. These advanced propulsion technologies could make human missions to Mars practical, reducing the journey time from 9 months to just a few months. Such capabilities would open the outer solar system to human exploration, making missions to Jupiter's moons and Saturn's rings a realistic possibility. Private companies are playing an increasingly important role in space exploration, bringing new capabilities and reducing costs. Companies like SpaceX, Blue Origin, and others are developing reusable rockets and spacecraft that make space more accessible than ever before. This commercial revolution in space technology is enabling new types of missions and expanding opportunities for scientific discovery. The concept of space settlements, once purely the realm of science fiction, is becoming increasingly realistic as we develop the technologies necessary for long-duration spaceflight. The International Space Station has shown that humans can live and work in space for extended periods, and future missions will test the technologies needed for permanent settlements on the Moon and Mars. Artificial intelligence and machine learning are revolutionizing space exploration, enabling spacecraft to make autonomous decisions and adapt to changing conditions. Future missions will rely increasingly on AI to navigate complex environments, analyze data in real time, and make discoveries that would be impossible with traditional remote-controlled systems. The study of astrobiology, the search for life in the universe, is expanding to include new types of environments and new definitions of habitability. Missions to ocean worlds like Europa and Enceladus will search for life in environments completely unlike Earth, while studies of extremophile organisms on Earth reveal the remarkable adaptability of life to harsh conditions. As we look toward the future, the possibilities for space exploration seem limitless. Human missions to Mars, robotic explorers searching for life on ocean worlds, telescopes that can directly image Earth like planets around other stars, and perhaps even interstellar missions to nearby star systems. All of these dreams are becoming increasingly realistic as our technology advances. The next few decades will likely see humans walking on Mars, robots diving through the ice of Europa, and telescopes that can analyze the atmospheres of Earth like planets orbiting other stars. Each of these achievements will expand our understanding of the universe and our place within it, answering ancient questions while posing new ones. As you settle into peaceful sleep tonight, imagine the future explorers who will venture beyond our world. Picture astronauts walking on the red plains of Mars, their footsteps joining those of the rovers that preceded them. Envision robotic submarines exploring the dark oceans of Europa, and telescopes so powerful they can detect the chemical signatures of life on worlds orbiting distant stars. The future of space exploration is not just about the destinations we will reach, but about the questions we will answer and the perspectives we will gain. Each mission expands our understanding of the universe and reminds us that we are part of something vast and magnificent. The cosmos awaits our exploration, patient and eternal, ready to reveal its secrets to those brave enough to venture beyond the familiar boundaries of our home planet. The adventure continues, and the best is yet to come. In the gentle darkness of space, countless worlds wait to be explored, countless mysteries wait to be solved, and countless wonders wait to be discovered. The universe is vast, but human curiosity is infinite, and together they will write the next chapters in the greatest story ever told, the story of exploration, discovery, and the endless human quest to understand our place in the cosmic tapestry. And so we reach the end of our cosmic journey, though in truth, it is not an ending but a gentle pause in humanity's eternal exploration of the universe. As the night deepens around us, and the stars shine their ancient light through the darkness, we carry with us the stories of brave explorers, both human and robotic, who have ventured beyond the boundaries of our world to touch the face of the infinite. We have walked on the moon with the Apollo astronauts, feeling the soft crunch of lunar dust beneath our feet and gazing back at the blue marble of Earth hanging in the star-filled sky. We have soared through the outer solar system with the Voyager spacecraft, witnessing the majesty of Jupiter's storms and the ethereal beauty of Saturn's rings. We have rolled across the red landscapes of Mars, searching for signs of ancient life in the rocks and soil of an alien world. We have discovered thousands of worlds orbiting distant stars, each one a unique experiment in planetary formation and evolution. We have explored the hidden oceans beneath the ice of Jupiter's moons, where strange chemistry might give rise to forms of life we can barely imagine. We have witnessed the birth of stars in spectacular nebulae, and pondered the mysteries of black holes that warp space and time itself. Through the eyes of our most powerful telescopes, we have looked back through time to see the universe in its infancy, when the first stars were igniting and the first galaxies were taking shape. We have traced the cosmic web that connects all things, from the smallest particles to the largest structures in the universe. We have found beauty in the dance of celestial bodies and meaning in the vastness of space and time. Each mission, each discovery, each photograph sent back from the depths of space represents humanity reaching out beyond our limitations to embrace the infinite. In our robotic explorers, we see reflections of our own curiosity and wonder. In our human astronauts, we see the embodiment of our dreams and aspirations. In our telescopes, we see tools for understanding that expand our perception beyond the boundaries of our senses. The cosmos is patient. It has waited billions of years to tell us these stories, and it will continue to reveal its secrets to those who seek to understand. The universe is vast beyond imagination, yet it is also intimate and personal, touching each of us with its beauty and mystery. We are not separate from the cosmos. We are part of it, citizens of a universe that is our home on the grandest scale imaginable. As you drift into peaceful sleep tonight, remember that you are connected to everything we have explored together. The atoms in your body were forged in the hearts of ancient stars. The calcium in your bones was created in supernova explosions. The iron in your blood was synthesized in stellar furnaces billions of years ago. You are quite literally made of star stuff, a living embodiment of the universe's creativity and complexity. The boundaries between Earth and space, between the familiar and the unknown, between the human and the cosmic, are not barriers but invitations. They remind us that we are part of something magnificent and ongoing, participants in a story that began with the Big Bang and will continue for countless eons to come. Our explorations of space are not just about reaching new destinations, they are about understanding our place in the grand narrative of existence. In the gentle darkness of your room, the universe continues its eternal dance. Stars are being born in distant nebulae, planets are forming around young suns, and perhaps somewhere in the cosmic vastness, other beings are looking up at their own night sky and wondering about the stars. We are all part of this cosmic community, connected by the fundamental forces that govern the universe and by the shared wonder that draws us to explore and understand. The future stretches before us, filled with new worlds to explore, new mysteries to solve, and new wonders to discover. Humans will return to the moon and venture to Mars. Robotic explorers will dive through the ice of Europa and search for life in the cosmos. Telescopes will peer deeper into space and further back in time, revealing the universe's deepest secrets. But tonight, as you close your eyes and surrender to sleep, you can rest in the knowledge that you have traveled farther than any human in history. You have journeyed through space and time, across billions of light years and billions of years, to witness the universe in all its glory. You have touched the infinite and found that it is not cold and distant, but warm and welcoming, filled with beauty and meaning that speaks to the deepest parts of the human spirit. The cosmos cradles us in its vastness, singing lullabies written in the language of gravity and starlight, chemical reactions and nuclear fusion, the birth and death of stars and the formation of planets and moons. This is the cosmic lullaby that has played for billions of years, and it will continue to play long after we are gone, a testament to the beauty and mystery of existence itself. Sleep well, fellow cosmic traveler. The universe watches over you with its countless eyes of light, and the stars will be waiting when you wake, ready to inspire new dreams and new journeys into the infinite depths of space and time. The adventure continues, and you are part of it now and always, in the eternal dance of cosmos and consciousness that defines the human experience. In the beginning was the Word, and the Word was wonder. In the end, there will be wonder still, as long as there are minds to contemplate the stars and hearts to be moved by the beauty of existence. Until then, we dream, we explore, we discover, and we remember that we are the universe becoming aware of itself, one star at a time, one world at a time, one moment of wonder at a time.